Welcome to a conversation about modeling using variation. This section is going to address the fact that when one thing gets larger, sometimes another thing gets larger. Sometimes when one thing gets larger, another thing gets smaller. And sometimes there are multiple things involved, and I just don't know what's going to happen. It depends on what the situation is. So I'm going to show you variations of those variations. Let's have a look. The first type of variation that I want to look at with you is called direct variation. And in this case, as one thing gets larger, the other will get larger, or as one thing gets smaller, the other thing's going to get smaller. And what facilitates that is what is called the constant of variation. And in this very generic equation, you're seeing that the variable, it's not a variable, sorry, the letter K represents the opposite of a variable. It's a constant. And that's going to be our constant of variation, or sometimes called the constant of proportionality. You've seen this before. You've seen it in the form of y equals mx plus b, and essentially that's what we're looking at, except where the b value is 0. All of a sudden y equals mx plus b becomes y equals mx. But in this case, we're going to replace the m value so that we can make it its own thing. Everything likes to be its own thing. We're going to replace m with k. And these problems are really nice because very often, well, the not so nice part is that very often these show up as word problems. But the good news about these word problems is that we should be able to translate them fairly efficiently and, dare I say, directly into a mathematical equation that we'll be able to work with. So stick with me here and you're going to see the rhythm of these types of problems. I think you're going to find them pretty tolerable, if I can say that. Let's see. So we're going to write an equation that describes the given English statement. So that's the translation process that I was just talking about. Then the problem typically gives us some, or will give us enough information that we can plug into the equation that we've created. And the only thing we won't know is our k value. So we will solve for our k value. And then, as number 3 says, we're going to take that k value and plug it back into the equation that we created. So now we will have some variables, we'll have some unknowns, but we'll have our k value. And then the last stage of the process, the problem will give us a little bit of additional information. It'll give us all of the unknowns, all of the variables except for one, and we will solve for that last remaining variable. That process is going to persist through all of the different types of these variation problems. Let's check it out. So in this example, it's not much of a word problem, but I do see some words, so we'll call it a word problem. We're being told that y varies directly as x. That's the statement that we're going to translate into an equation. And when we see y varies, I don't want to use red. I like starting in blue. Let's use red to highlight some things. Y varies directly. So the y part is obvious. The varies directly part is this part here, equals k times. The next thing that we're going to look at, the next type of variation, is going to be varies inversely instead of varies directly. I just told you that varies directly means k times. In the next example, we're going to see varies inversely, which is going to mean k divided by. So we do need to know how to perform these translations. Okay, so y varies directly as x. There we go, we've got our equation. As promised, we're going to be told everything except for our k value. So let's plug these numbers in. 45 is equal to, don't know what k is, times the given x value of 5. We'll divide both sides by 5 to find that 9 is equal to k. So we've got our k value. We're going to take this k value, plug it back into the equation that we designed. And now we've got y equals 9x. And then the last stage of the problem, we're given all but one of the variable values. In this case, we're not being told our y value, that's what we have to find, but we are given an x value. So let's plug in that x value of 13. And then we can do our arithmetic and find that y equals 9 times 10 is 90, 9 times 3 is 27, 90 plus 27 is 117. And that's our answer. You can bet that there are more difficult versions of this problem, but we're just getting warmed up. Be aware that it's possible for a direct variation problem to involve powers. So it can, y, as it says right here, y can vary directly, so that's y equals k times what? The nth power of x. So we're seeing here that our variable, whatever it happens to be, here they're describing it as x, can be raised to a power. All right. So we're not going to see an example of that worked out, but just be aware that it could show up. Inverse variation, as I mentioned before, is the next type of variation that I want to look at. And here we have y varies inversely as x. So have a look in this blue box right here. Let me change the color of my highlighter. I want to make sure you see this. Y varies inversely as x, or y is inversely proportional to x. It's very possible that you're going to see either one of those two versions of a statement show up. That language is pretty interchangeable. It does result in a rational function. We just finished talking about rational inequalities in the previous video. But we're going to use the same procedure to solve inverse variation problems as we did to solve direct variation problems. I told you were going to like the consistency aspect of these problems. So here we're being told that y varies inversely as x. Let's translate. Y varies inversely equals k divided by as x. So x goes in our denominator. Step 2, plug in the given information and solve for k. So y is 9 equals k divided by x value of 3. Solve for k. Multiply both sides by 3 to find that 27 is equal to k. Plug that into the original equation that we designed. Y equals k over x becomes y equals 27 over x. And then finally, we will plug in the last piece of given information. This is I've been saying step 3. I think in the notes above it was actually step 4. But anyway, we're going to plug in our x value and solve for y. So y is equal to here 27 divided by a given x value of 6. You're going to want to simplify that as much as you can. So our final answer, when we simplify reducing by 3, we get 9 halves. 9 halves as a decimal is 4.5. Answer A. And I believe the last type of variation that we're going to look at in this section is combined variation, sometimes referred to as joint variation. So you might see language that says, here this says, A varies directly as B and inversely as the square of C. Unless I'm mistaken, I don't like to misspeak. So we will actually see joint variation as a separate version of these variation problems. So we're just going to subtitle this one combined variation, and we are seeing varies directly, and we're seeing inversely in the same statement. Let's see if we can take this sentence and turn it into an equation. A varies directly, so equals k times, varies directly as b, so we'll multiply it by b, and inversely, so now we need to introduce a fraction, so let's divide by the square of c. I see so many students, semester after semester, read this statement, the square of c, and for some reason they read it as the square root of c. It's different. Square root, you know what a square root is. If they wanted you to take the square root of c, it would say the square root of c, but it doesn't. It says the square of c, which we should interpret as c squared. So that's step number one. We've got our equation. Let's plug in some given information that we can use to help us find our k value. So we have an a value of 7 is equal to, we don't know what k is, times a given b value of 9 over a given c value of 6, which we have to square. And now we have to solve for k. Now we could multiply both sides by 36 right away. In fact, I don't know, let's do that. 7 times 36, and let's divide both sides of our equation by 9 so that we've got k all alone. Now the 36 and the 9 reduces, so I'm going to reduce this to a 4 before I multiply the 7 and the 36. Which is great because now 7 times 4, I can do that in my head. I stink at arithmetic and even I know what that is. It's 28 and that's our k value. Nice. So we can take the k value and plug it back into the equation that we designed. That's an arrow, if you believe it. If I draw enough stuff over the top of it, it won't have looked so bad. Now it looks bold. All right, so our original equation a equals, we've got a k value of 28 times b divided by c squared. So that's our original formula or equation with our k value plugged into it. And now this question better give us 2 out of 3 pieces of information. They want us to find a, so that's what they're not telling us, when b equals 4 and c equals 8. So they did indeed give us 2 out of 3 pieces of information. 28 times a b value of 4 divided by a c value of 8, and that 8 has to be squared. I think I'll keep going vertically. A is equal to, now 28 times 4 over 8 squared. We can think of this as being over 64. That's made up of all 2's. So now let's see, 28 is 7 times 4. And there's already a times 4 up there. And in the denominator, we have 8 squared, which is 64. Now 64 happens to be 4 times 4 times 4. Why do I know that? Remember, I'm a math teacher. You're a math student, so that might not have jumped out at all of you. However, realizing that 64 is 4 times 4 times 4 is helpful because it makes it really easy to reduce this fraction to get our final a value as 7 over 4. If you didn't know that 64 was 4 times 4 times 4, my recommendation is always to try to reduce your fraction as much as you can before you start multiplying stuff together and making your numbers larger. So you might consider writing this as 28 times 4 over 8 times 8, and then doing a little bit of reducing here. The 4 over 8 reduces, leaving you with a 2 in the denominator. The 28 over 8, it might not jump out at you that they're both divisible by 4, but they're both even numbers, so divide them both by 2 first. This turns into a 14 over 4, and then you have to pause long enough to realize that those are both even numbers again. Divide top and bottom by 2 again, the 14 turns into a 7, the 4 on the bottom turns into a 2. Now the only thing that remains on the top is a 7, and on the bottom in the denominator you've got a 2 times a 2. And there's your 7 over 4. So just a couple of tips about how to work through these. If you're not using a graphing calculator that you can type this into and then have it take your decimal and turn it into a fraction for you. And I think there are some scientific calculators that'll do that also. But if you don't have access to one of those, you need to know how to reduce this stuff on your own. So that's why I went through those motions. Here it is. This should be our last type of variation called joint variation. And it's a variation in which a variable varies directly as the product of 2 or more other variables. So this is going to be a equals k times something, and then times something again. Let's see how it shapes up. Kinetic energy varies jointly. Ooh, all right, so I'm going to use capital K to represent kinetic energy. It varies jointly. When I read varies jointly, oh, I can't use K for kinetic energy. Let's change that K to a capital E for energy. Kinetic energy varies jointly. When you read varies jointly, you need to be able to translate that from English into math. It's like code for put an equal sign and then a K and then times, and then you're probably going to be multiplying it by at least a couple of things. Excuse me. This is like my 7th video in a row, so I'm starting to lose my voice. So it varies jointly as the mass, so we'll multiply it by m, and the square of the velocity, v squared, not the square root of velocity, it's the square of velocity. And then there's a period, so that's the end of the sentence. We've created our equation. Great, so now we're going to be given enough information to help us solve for K. Let's plug in some numbers. A mass of 8 grams equals K times 8, and a velocity of 3 centimeters per second. So there's a 3, and we have to square it. Has a kinetic energy of 36 ergs, which, as I recall, is a real unit of measure. And there we go. The only unknown that we have is K, so let's solve for K. We're going to take the 36, and we're going to divide both sides of our equation by 8, and we're going to divide both sides of our equation by however you want to do that. If you want to divide it by 9, that's okay with me. If you want to divide it by 3 times 3, that would be okay also. Can we simplify this fraction? Well, 36 divided by 9 is 4. And then the 4 and the 8 are going to reduce to a 1 over 2. So our K value is actually 1/2. Let's plug that back into the equation that we designed. Kinetic energy is equal to our K value of 1/2 times mass times the square of velocity. And now we go find the other pieces of given information. And I'm going to keep working up here so we can stay on screen. All right, find kinetic energy. Great, we're solving for capital E. That's all alone on the left-hand side of the equation already. Equals 1/2 times, all right, I'm ready. Give me the mass, 4 grams. And I'm ready, show me velocity, 6 centimeters per second, and we have to square that, so there's a 6 squared. So E is equal to, well, the 1/2 times 4, this is going to turn into a 2. So we've got 2 times 6 squared. 6 squared is 36, and 36 times 2 is 72. And I can't help myself. I just had to write ergs. So strange. Who comes up with this stuff? All right, there's my final answer in a box, and let's just make sure there aren't any other little surprises waiting for us down here. And that is it. We have hit the bottom of this set of notes. And I'm pretty sure that puts us at the end of a chapter. So if you are in my class, then I thank you very much for joining me for this chapter. And if you're not one of my students and you found this video, I thank you very much for watching. I encourage you to like and subscribe, and I'll see you around. Thanks.